two, that the previous class, so class 1, was recorded and it was posted online on YouTube. So if you go to Acorn, I posted the link up there as well. So if you ever want to review the previous classes, you can go there. We did not record class 2. That was the co-op one. That was one on Wednesday. So the students that were there didn't want to be recorded, so that's fine. It's not course material anyway. So there you go. So what we're going to be looking at in this chapter is we're going to be looking at rates of reactions. We're going to be looking at chemical kinetics. And really, this is an extremely important question in chemistry, because what this tells us is how fast something happens and what factors control how fast a chemical reaction can happen. And this is important in sort of all areas where chemistry applies, whether it's in sort of industrial settings. If you're trying to do reactions, you want to know how quickly you can convert materials to products. It matters in environmental chemistry because you want to know how quickly things in the environment might degrade. It matters in biochemistry because biochemical reactions are all timed, like they all have a very specific rate. And in fact, speaking of COVID, if you have a fever because you're sick, what that does is it raises your body temperature. And as a result of raising your body temperature, that changes all of the rates of all of the biochemical reactions that happen in your body. So what we're going to be doing in this unit is looking at quantitatively, so we're going to use, describe using math, how the rates of reactions can be understood, how we might be able to categorize them or explain them, and use what we get out of that to answer some practical questions about some chemical reactions. So you can see in this picture right here, there's a huge variation in rates of chemical reactions. So we have the barbed wire rusting, and if you put iron out in the environment exposed to water and air, it will just on its own start to rust, although it's a fairly slow process, right? Like this would take on the order of years, whereas other reactions can take seconds, or in some cases we'll see like nanoseconds, like extremely fast reactions. Geologists might consider the rusting of that piece of wire a fast reaction. So there are other reactions that take place over thousands of years or millions of years, which are of geological importance. So what we need to be able to do, first of all, is understand how, if we're conducting a chemical reaction, how we might be able to monitor how fast the reaction's happening, or monitoring sort of the progress. Is the reaction half done? Is it 80% done? And so on. What are some methods we can use to do this? And there are a huge number of variations of this. There are many, many different ways, and depending on the type of reaction, how we follow the reactions happening. So I'm only going to talk about one or two just to give you an idea, but these are not exhaustive. There's lots and lots of ways of doing this. I think sometimes too, like if you're baking a cake, right, or brownies or something like that, that's a chemical reaction. It's called the Maillard reaction, and it's in the oven. It's actually not just one reaction, it's lots of reactions. But how would you monitor the reaction progress there? You might look in the oven periodically and see how much it's risen. Towards the end, you might stick a knife in and see if there's any batter left that's not cooked. These are all methods you would use to monitor the progress of some particular reaction. But for us, we want to do it quantitatively. What I described there for the cake is not quantitative, right? You can't stick a knife in a cake and say, oh, it's 86% complete, right? But we can do that in many cases for many chemical reactions. So the example that's on the screen that you can see right now is the reaction of calcium carbonate reacting with HCl. And what that reaction produces is calcium chloride, which is a salt, with water, which is, of course, a liquid. But then the last product we see is carbon dioxide, which is a gas. And gases tend to bubble out of solution if they're produced in a reaction. So in this particular reaction, what you'd expect to see if you were watching this take place is the calcium carbonate and the HCl would start to bubble. It would fizz, right? And bubbles would be produced. So what you could do then, and you can see this in the picture right here on the screen, is they've taken the reaction flask and they have on top a stopper with a hole, and the hole is connected to a syringe. And with the syringe, you could measure exactly what the volume of gas is inside the syringe. So what happens as this reaction proceeds is the CO2 bubbles out. Of course, it's gas, it takes up space, and it causes an expansion, right? It causes the plunger to be pushed out of the syringe. And what you can do is measure at any point in time exactly how much volume, how much increase in volume there's been, which in other words is how much CO2 has been produced. And then of course, as the reaction goes on, time and time later, it'll be further and further down the side of the syringe as it opens up and accepts all this gas. So what this is showing then is this graph is the volume of carbon dioxide gas that's produced as measured in the syringe versus time. And you can see, it starts to rise quickly, and it kind of, over this way, it slows down as the reaction's about half done, and then it starts to taper off. And the last little bit of volume takes quite a long time to actually fill up. Another thing you could do for the exact same reaction is forget about this syringe, take the top completely off, and put the whole thing on an analytical balance. So what happens is the CO2 bubbles out, is the mass of the solution decreases because you're losing mass, you're losing the carbon dioxide. And so what's happening there is the mass will decrease. And then you could follow the course of the reaction, because eventually when the reaction is done, the mass will stop changing. And there you go. You'd have a sort of a measure of the sort of percent completion of this reaction versus time. So these are just two methods for this particular kind of reaction. Lots of other ways. Sometimes you see reactions that either produce a color or maybe a color disappears. You could use a spectrometer to follow how much color has been produced or how much color has disappeared, and so on. There's lots and lots and lots of different chemical methods we can use. Basically, anything that can measure something about a chemical system could be used to follow a reaction. Okay, so this is what we call a kinetic profile. It shows you basically the amount of reactant that's left in a reaction over time. So initially, when the reaction starts, you have a large amount of the reactant, a lot of it, and then the reaction starts. The reactant starts to disappear and produce products, and you can see that the amount of reactant drops. And in this particular example that you see, this blue curve looks to me like it follows an exponential function. And we see that in a lot of chemical reactions, but not all. Some don't. What you can say, though, about this curve, this blue curve, is at any point in the reaction, the slope of that curve, which would be, I guess, the first derivative, the slope at any point along this curve will be equal to the rate of reaction. So at the very end of the reaction, the slope is very small down here, and at the very, very end, the slope of this reaction is 0. And when the slope of the reaction is 0, that means the rate of the reaction is 0. It means the reaction is stopped. So this curve, how it starts out steep and then kind of plateaus out, would represent a reaction that starts out really fast, and then the reaction kind of tapers out as it goes on. So what's an example of a reaction like this? I don't know, something like maybe I use this example later in the slideshow, but I'll use it now, is popping popcorn. If you had a pot with hot oil and you chucked in, I don't know, a half cup of popcorn kernels, and you can tell every time a reaction happens, which is a popcorn popping, you hear the pop, right? You can hear it yourself. What would happen as soon as you threw it in and it starts to heat up very quickly, you'd start to get lots of pops because there's lots of popcorn kernels unpopped left. And then it would proceed quickly. And as that popping goes on, and I'm not sure if you've ever, well, probably everyone here has popped popcorn before. But when you get towards the end, the pops become much less frequent. You get an occasional pop here and there. And then eventually, if you've gone long enough without hearing a pop, you are assuming you're sort of at the end of the reaction over here, and you stop it, right? You take it out. You don't want to burn the popcorn that you already made. So what we can say then is that the rate of the reaction at any point in time will be equal to the slope of this curve, which is the change in concentration of reactant over the change in time. And as here, we're going to apply a little bit of calculus understanding here. As this time interval, this change in time in the bottom, approaches 0, we would say that the rate approaches, it's the gradient, or it's the tangent to the line at that point in time. We would say that we would call that an instantaneous rate. The rate is true, it's that rate at one point in time in the reaction, but a second later, the rate is going to be something different. In this example, that rate will be something slower, if you go a little bit. So, a moment after, let's say we're here in the plot, the tangent might look something like that. It'll be a little bit slower, and therefore a slightly slower reaction. This is the same idea, right? This is just applying it to not disappearance of starting material, but formation of product. So formation of product begins to form rapidly at the start. The instantaneous rate at the start of reaction, we call the initial rate. And it's whatever the slope of this red line is, which is tangent to that curve at time 0. But that instantaneous rate almost immediately starts to slow down as the reaction proceeds. And by the time you get to the end of the reaction up here, we see a tangent line that's essentially horizontal, which is 0 slope. All right, so let's apply this to an actual real reaction. This is the decomposition of hydrogen peroxide. So hydrogen peroxide would be that material, that liquid, a 3% solution you can buy in the drugstore. And if you ever had a cut as a kid, you might have had this no, I don't want to use that word, poured over the cut, and you might have seen it start to fizz and bubble and so on. That's this reaction taking place, is decomposition of the hydrogen peroxide into water and oxygen gas. So this would be a reaction you could follow by, you could look at the amount of gas that's produced according to pressure. You could look at change in mass if this reaction was left open, because you're going to lose mass from oxygen bubbling out of solution. So if you're looking at the rate of this reaction, you can look at it in terms of disappearance of the reactant, which is hydrogen peroxide, or appearance of either the oxygen or the water. Because we have two different products, you can follow one or you can follow the other. Water appears to be generated, well, it is generated twice as fast as the oxygen, just because of the stoichiometry of the reaction, right? We get 1 molecule of water for every molecule of H2O2, but only half a molecule of O2. So if you look at that, whatever water is, it equals 2 times whatever oxygen is, because of the stoichiometry. So the rate of the reaction there would be equal to, at any point in time, the first derivative of the slope, of the green curve, which is disappearance of starting material. And we have a negative sign in front because it's a reactant that's disappearing. Or we could look at it in terms of the production of water at any point in time. It'd be the slope of that line, that blue line. And that's positive because that is a product that's being produced. Or you could take the oxygen one and double that. And we have to double it because of the stoichiometry of the reaction. So what we can say in general is if you have a reaction, A plus B goes to P plus Q, where the small a's and b's and the small p's and q's are the coefficients of the reaction, like the numbers, the 1, 2, half, whatever. we can say then that we can express the rate of that reaction at any point in time, the instantaneous rate, in terms of disappearance of A, and we divide or multiply by 1 over the coefficient. And this is, again, the reason we're multiplying by 1 over the coefficient in every case is to account for the fact that these may appear or disappear at different rates just because of the stoichiometry of the reaction. The overall reaction is a single reaction that's happening with a single rate. So if we're looking at a particular reactant or product, we want to normalize it for whatever the coefficient is. So we can express the reaction rate in terms of disappearance of A. We can express it in terms of disappearance of B, or we can express it as appearance of product P or appearance of product Q. So there's 4 different ways that we could follow this potential reaction. We don't need to follow all 4. You just need to pick one of those 4 that you can measure easily by pressure or mass or whatever, and then you can express the rate of the reaction like that. Reaction rates are typically represented in units of molarity per second, which is the same thing as molarity times seconds to the -1, which often you see expressed like this as well, which is moles decimeters to the -3 seconds to the -1. Cubic decimeter is a liter. So these 3 units are all equivalent. They're all moles per liter per second. You can see sometimes rates expressed in other units as well. Like if we had a slow reaction, that it wouldn't be appropriate to use seconds. Maybe it's days, maybe it's years, right? A geological reaction, you'd probably express maybe in years or even centuries, who knows? But yeah, just make sure that what you always have is a unit of concentration over time. All right, so we're going to begin by looking at what we call elementary reactions. And basically, elementary reactions are reactions that take place as a result of a single collision. So this was actually a big aha moment for me. I remember as a chemist, I didn't realize why sometimes molecules would react with other molecules, why reactions took place at all, when to expect a reaction and when not to expect a reaction. And I forget when I learned this, but it was the idea that in order for a reaction to take place between 2 molecules, they have to physically come into contact with each other. They have to collide. And maybe that's obvious to everybody here, but it was not obvious to me for whatever reason. But it's true. So if there's a collision between two molecules, that allows for a reaction to take place. So an elementary reaction is just a reaction that involves a single collision. Okay, either one thing actually can just split in half, or 2 things can collide with each other. These would both be examples of elementary reactions. So on the screen, you can see we have this molecule, which is methyl bromide, and here we have cyanide ion. So you can have a reaction where these 2 collide with each other, and then after the reaction, products are formed. And you see what's happened is the cyanide has replaced the Br on the CH3, so this is a new product, and the bromide that was previously attached to the carbon is now gone. So this is a reaction. It's the balanced equation is written down below. This is a reaction we would learn in organic chemistry. It's called a SN2 reaction, but it involved just a single collision. We call this an elementary reaction. The other type of reaction that's not an elementary reaction, we often call a complex reaction, and it just means there's a sequence of collisions. So there's several elementary steps that would make up what we call a complex reaction. And probably most reactions that we're used to are actually complex reactions, involve many steps. Think about in our bodies, if our body, say, produces cholesterol, that has like hundreds of steps. It's a very, very, very complex reaction, as many biochemical reactions are. So what we can do actually is describe the rate of an elementary reaction like this, or any elementary reaction, in terms of something called a rate law, which always will look like this. It looks like the rate of the reaction is equal to some constant K, which we call the rate constant, multiplied by the concentration of the first reactant, multiplied by the concentration of the second reactant. If there happens to be a third reactant, which there isn't in this example, but if there was, we could have a third reactant there, and so on, right? So basically, to construct the rate law for an elementary reaction, it's just always just going to be rate times some rate constant K times, and then it's just going to be whatever is colliding in that step, and it'll look like that. So what this tells you is the rate at any point in time in the reaction, assuming you know the concentrations of everything that's in solution at that time. So if you look at your products, CH3Br and Cn minus, just put those concentrations in, multiply them by K, and you get the rate at that instant in time. And it actually makes sense why these reactions often have reaction profiles that look like this. Because as the reaction proceeds, you start to run out of these reactants, right? These reactants are going away. And because those reactants are going away, the rate slows down, because the rate depends on how much of the reactants are there. Which also kind of makes sense if you think about it, because we have these reactants coming together and colliding with each other. Those collisions are going to be a lot less frequent if you have a lot less reactant there to be colliding. So if you increase the concentration, you increase the number of collisions, and you increase the rate of reaction. This rate constant, by the way, it's a constant for that reaction no matter what concentrations of the reactants that you put in. It'll work for any concentrations that you want. But I will say that the rate constant is specific to a particular temperature. So if the temperature changes, you have a new version of K as well. K will fluctuate with temperature, but if you're at a constant temperature, it'll always be a constant regardless of what point of the reaction that you're in. All right, so remember that the units here that we're looking for rate is always molarity per second, or molarity times seconds to the -1. The units for concentration of our reactants is always in units of molar. So you can divide to figure out what the units of K are going to have to be in this particular case. So in this example, the units of K have to be molarity to the -1, seconds to the -1. And that's because if you take molarity to the -1 times molarity squared, because we have molarity here and molarity here, that's going to be equal to molarity seconds to the -1, which is the unit we have to produce for rate. So just wanted to say that the units of K can change depending on how many different reactants we have that are reacting with each other, as we'll see in a little bit. Okay, another thing I want to define right away is something called reaction order. And what reaction order is, I mean, it's kind of not a great term if you ask me, because order to me implies sort of the sequence of events that take place, the order of events, but that's not what we mean here. When we're talking about order, what we're really talking about is how many things are colliding in this particular elementary reaction. So remember this, elementary reactions equals one collision. So let's say we have a reaction where we have A plus B going to products. We will have the rate law for the elementary reaction, K times A times B. If, let's say there's a 2A, so if there's 2A plus B to products, that would be the same as A plus B, the products. So the rate is equal to K times A times A times B equals K times A squared B. And this is always true if it's an elementary reaction. So what we would do is describe the order of this particular reaction as being the number of things that are colliding. And if you look up here, you could say, well, the order is going to be 3, right? There's 3 things that are colliding in this reaction, this elementary step, A plus B, which, if you're looking up here, is just these superscripts. Remember, there's a 1 there, it's not shown. It's the superscripts added together. So you can either look to see what is actually reacting in the elementary step, count them up, or look at the rate law and add the exponents up together. And if there's nothing shown there, the implication there is that there's a 1. So 2 plus 1 is 3, and that would be the order of the reaction. So we could have reactions that are first order, second order, third order. A first order reaction would have a rate law that would look like rate equals K times just a single reactant. A second order would have 2 reactants, maybe, like A squared. A third order, you could imagine it could be A cubed, or you could imagine something like B, and maybe even C. 3 things collide with each other. So whatever those exponents are, if you add them up, whatever the number is, that's the order. They don't have to be all different. They could be the same as you see in this example, or they can be all different like you can see in this example. One other thing you can tell is if you look at the units, right? Rate is always molarity seconds to the -1. Concentration is always molarity. So in this case, you can tell for the first order, the units would have to be seconds to the -1 for those to multiply together to give you the correct units for rate. So for first order, the units of K are S to the -1, seconds to the -1. For a second order reaction, the units are molarity to the -1, second to the -1, and so on, right? Third order would be this, and you could figure it out for any other order that you see. So we're going to start out by looking at a little more detail at first order reactions. And I'll say this right from the start is first order reactions are extremely common and second order reactions are extremely common. Slightly less common, but still fairly common, are what we call zero order reactions. Reactions that are order of 3 or higher are extremely rare. And the reason for that is that it's just very unlikely to have 3 molecules all collide at the exact same time in the exact correct orientation for a reaction to take place. It's just improbable, so it's difficult for it to happen. You can make it happen sometimes if you really have extremely high concentrations of things and very high temperatures, or you let the reaction proceed for a very long time. But imagine, you are walking downtown in Halifax on a random weekend day. And what is the chance that you're going to run in randomly to one of your best friends from elementary school? There's a chance, right? It could happen. It may not be a very high chance, but let's say there's a chance there. Now think about it. What is the chances that you will run into your best friend from elementary school and then your second best friend from junior high school in completely unrelated events, but at the exact same time in the exact same place? Chances of that become much, much lower, right? Of those 3 things happening all at the same time in the same place. Not impossible, just a lot less likely. So the same thing is true with a chemical reaction. To have 3 molecular species all hit each other at the exact same place, the exact same time, and with the exact same orientation, right? They have to have the perfect orientation for a reaction to happen sometimes. That's just not very likely. First order reactions, though, super likely. First order reactions just involves a single molecule undergoing some reaction. In this case, we have iodine I2 falling apart, breaking in half to make two individual atoms of I. This doesn't require any particularly high level of luck, right? It's just if the energy is there to break that bond, this reaction will take place. Doesn't require a chance collision between two things or more than two things. So the order of this reaction is 1, because it's a first order reaction. Only one molecule is involved. And we still call it a collision, I guess, or an event. The collision might be with a solvent molecule that's not reacting. Something has to provide that energy through a collision for the reaction to happen. But we could say that the rate law for this reaction is going to be equal to whatever the rate constant K is, times the concentration of I2, which is the starting material, which is the reactant. And we know right away that the units for K are going to be s to the minus, come back. S to the minus 1, seconds to the minus 1. So the reason for that is rate is molarity, seconds to the minus 1. This is molarity. Cool. Because there's only a single molecule that is reacting in this particular step, in this reaction, we call this reaction unimolecular, which stands for one molecule. So we could either call this reaction first order or unimolecular. Those two terms mean essentially the same thing. Okay, just hang on 1 second. My daughter is at the dentist and she's texting me something. I'll say what? See if she gets back to me. First order reactions, yeah, there we go, we're good. First order reaction looks like this. At the beginning, you have a high concentration of your starting material. So this, again, the rate at any point in time on this graph is going to be equal to K times the concentration of I2. So at the start of the reaction, your concentration, so when I say concentration of A, what this really is concentration of I2. When the reaction begins, this red value here is concentration of I2 0. So that just means that 0 means at time 0, initial concentration of I2. So the initial concentration is whatever that number is. Then as the reaction proceeds, the concentration of I2 drops. Because the rate depends on the concentration of I2, we expect the rate to get slower as we start to lose I2 here. So we would say the rate at this point in time would be the tangent line at time 0. And let's say the reaction proceeds to 50%. So let's say we go to this point, which is, I guess that would be the initial concentration over 2, when the reaction's half done. And move over, we get to this point in the graph. So we're down to half the concentration of I2. The rate at that point is going to be equal to the slope of the tangent line at that point. And that rate, you can see, is going to be less steep than it was at the start. It's going to be a slower reaction. In fact, it's going to be exactly half as fast if the concentration of I2 is exactly half as fast. If you go down again, let's say we go down to the reaction being 75% complete. That would be when the initial concentration is 1/4 of what it started out as. That might be this point right here, say, if you drop that over. Your tangent line here again. Rate is whatever the slope of that line is. That slope, again, is lower than it was previously, so the rate is getting slower and slower and slower. There we go. So basically, I think we've come around to, we've attacked this mathematical description or this graphical description of this reaction. from a number of different angles, how we can understand the rate, how we can understand the rate law, and what that actually means. All right, so what's an example of first order kinetics? I told you before an example of first order kinetics was popcorn popping, and actually someone has actually studied this. What they did is they recorded the sound of popcorn popping, and they took the popcorn, heated an oil up to a certain temperature, and then threw the popcorn into the oil, and then they recorded the audio of what they heard, and they ran the audio through software that could detect every individual pop. And so they knew how many kernels they put in. Every time there was a pop, they knew there was one less kernel remaining. And this is the data they got. They always threw in 100 popcorn kernels. And what these lines represent are different temperatures of the oil. That was 180 degrees. This one was 190 degrees. And they were trying to determine what the best temperature was for popping these things. And what you could see at the beginning, as soon as they threw it in, there's sort of a lag of time for all cases, regardless of the temperature, where nothing really took place. And that's because when you throw the popcorn in, it's cold, it has to absorb the heat, and the reaction doesn't start until it gets warm. And then what you can see, though, is that, for the 180-degree reaction, it follows this line down here. At 190, now I think I got these reversed. I think this was the 200, and this was the 180. Yeah. For the next one, it follows this red line, and then the last one follows this red line. So if you ignore that initial sort of delay, and the delay seemed to be longer for the coolest one, which is 180 degrees, they did as well for 170, but didn't see any pops. So there's another one there that they didn't get to. What happens is all three of these follow what we call an exponential decay. All of these match the rate law. Rate equals K times concentration of kernels. How do you spell kernel? E-L-S. They're all first order. If you take any point in this curve, like here, the rate at that point in time is the tangent. The rate at this point in time is this tangent, which is slower, right? Less of a slope. And you can describe exactly, mathematically, that particular process. So it's first order. It follows what we call first order kinetics. And when you think about it, it should follow first order kinetics because it's a single popcorn kernel popping. It doesn't involve something else reacting or colliding with it. It's an independent event for each popcorn kernel, which is why it's a first order reaction. It doesn't involve two popcorn kernels merging somehow or anything like that. So we see it as a completely first order process. The other thing we see is that at the lowest temperature at 180, the reaction, let's say the time to get the reaction to say 95% completion is probably maybe somewhere around 450 seconds. Whereas at the higher temperature, 190, 95% complete is probably almost half that, like 200 seconds. And then at the next higher temperature, 200 degrees Celsius, it's more like 80, 90 seconds, something like that. So the reaction is getting faster at higher temperatures, and you can see that graphically by this slope. They're all still the same rate law, but the K is changing, and that's causing the slope to push towards the right here. So this would have the slowest or smallest K, and then this one would have the largest K. And you can imagine what would happen if you increased it up to, say, 210, is you might see another slope that's up here, right? Something like that. So we see this a lot. You can follow these reaction profiles regardless of the temperature. Cool. Let's take a peek quickly at second order, and I think that's all the time we're going to have today. If you have an elementary step that's second order that involves two things colliding, in this case, I'm going to be looking at A plus A, so two of the same thing colliding to make a product. And it could also be two different things. This is also second order. However, the math becomes a lot more complex when it's A plus B. So we're not going to deal with those types of second order reactions to the same level of detail. We'll be looking at A plus A. We'll see this later on in the chapter. Okay, so for a second order reaction, the rate law would look like this, where the rate is equal to K times A, or A squared. And that's because it's, second order. We would call this a bimolecular reaction because there's two molecules that are reacting in that. And remember, we're still talking about elementary reactions, meaning we're still talking about just a single collision, a single reaction step. And I really want to underscore that because we're going to come back to complex reactions. So here we go. Here's the A plus B. Here's the different one. And we have the rate law again. And the order is still 2, right? Still second order because we have 1 plus 1 equals 2. Great. And this is just me saying again that the probability of having a rate law with a higher order than 2 is extremely unlikely for an elementary step. Almost every elementary step is either first order or second order, and that's just the way it works. All right, so what we're going to move into next is we're going to talk about complex reactions, because complex reactions are just a sequence of elementary steps. Typically, a sequence of steps that are first order and second order, and we call these complex reactions. And I sometimes think about this as like a flight, where if you are in sort of city A and you want to travel to city B, there's a number of different paths you could potentially take. You could get a flight that goes direct from A to B. That would be a single step. If a reaction happens in a single step, it's an elementary step. It's an elementary reaction. But if it takes place as the result of a series of stopovers, like you see here, you know, we have 1 to here, 1 to here, 1 to here, and 1 to here, and then finally the last leg. These steps take place in legs. Complex reactions are reactions that take place in these small steps. Each individual step is an elementary step, like we've been looking at up to this point, but collectively, the overall reaction is a complex reaction. So everything we've learned so far about elementary steps applies only to the individual steps, not to the overall process. So we're going to be, next class, tackling how to think about an overall complex reaction by piecing together these segments, these elementary steps. Which reminds me of, I think, the worst flight I ever took, which was, in terms of steps, I've had other bad flights for different reasons, but I was flying from Halifax to Victoria, BC, and I was a student and I was trying to get the cheapest flight I could, and the flight started in Halifax. I think it went Halifax, Moncton, Ottawa, Toronto, Calgary, Vancouver, Victoria. So it was like up, down, up, down, up, down, up, down, up, down all day. It took like 15 hours, and yeah, I was grumpy by the end. So that's, I think, where we're going to leave things today. We're going to come back. We'll start again with complex reactions in our next class. And until then, you guys can all have a great weekend, and you can live free, knowing that you have no assignments or anything like that to worry about in chemistry. Maybe what I'll do, though, actually, is if I get the time, I might try to get an assignment up early and give you guys more time to work on it. And that way, you know, the due date will still be what I said before, but if it's open earlier, then if you have some free time early, you can start to get at it. Sound good? Perfect. Everyone's still with me here? Everyone's still awake? Happy? We'll never know. Oh, I gotta thank you. Great. Glad everyone's here. Glad everyone's doing well. I'll leave you now for the weekend and have a great weekend. And we meet again first thing Monday morning. I don't know yet if that class on Monday morning can be live or not. I'll know more as things go on. But as I learn more about the situation, once I think they figure stuff out, I'll certainly let you know. I'd say maybe the default would be to have it online, but it could be in person too. We'll see. I'm feeling good, no symptoms, so I'm quite sure that I have nothing to worry about. But yeah, we're playing it safe right now. Awesome. Thanks, everybody. Have a great weekend, and we'll see you on Monday.